Jai Hind all. This is Assistant Professor Gagandeep Singh from Ajay Kumar Garg Engineering College. This is a complex lecture series on VLSI technology. The course code for this subject is KEC 053, and this topic is the first complex topic. So we will cover the basic of the VLSI technology that should lay down some foundation for this course. So to create the foundation of the course, we should know how the development of the IC technology has been there since the invention of the devices, solid state devices. So if we discuss about the history, then the first history comes when the first IC device comes when there was vacuum tubes. The vacuum tubes, which were invented by the Sir Lee De Forest, who has invented vacuum tubes to create the switching effect, switching of the electronic switching. So after that one, in 1928, a paper was published by JE that we can create some solid state device for the same switching effect that was given by uh, the vacuum tubes. So they create a drain, source, and the gate arrangement using the aluminium, silicon, and aluminum and copper compounds. So with this idea, there was a spark that we can create some devices using the silicon, using the some materials in the with some particular materials. So first, after 1928, the first transistor was created by Shockley, Sir Shockley, and his team. They create a germanium transistor, which was not a small one like we see in today's life. It was a bigger component which can be with some rough layerings. So there is a drain, source, gate, which was noticed very small in size. If we see, this is the first gallium BJT that was prepared using the different materials. Here they have used aluminium and its components, copper, for the conduction, and the all purposes that are solved today is by the silicon. So after that one, this was the first IC that was prepared in 1958 by Kilby. Sir Kilby has prepared some components, some transistors, MOSFET, FET with some R and L components on the same on a one chip. So they have created RL. This is R and L, R and C capacitor, and the resistance that are on the same wafer. So RC circuit was the first circuit that was on one single that was first integration with the BJT, with the FET. So this FET has the three layers, which was then connected with the R and C on the one frame, on the one wafer. So with this circuit, we can use anywhere where we need RLC with RC with some feedback of the BJT. So active oscillators, we use RC filters. So such kind of circuits we use this. We can use this first IC. So from here onwards, there were the first IC was started. So we have seen that from the very beginning, when some non solid state device was formed, which was a vacuum tube to an IC, there was some quite a long period. So after this one, this was the IC that was created. This was the IC which was created by the such Kelby. So this has resistance transistor and the distributed capacitor and the transistors. So these are the things that were included in this IC. For this one, he was also given some Nobel prizes, and it was cited by a Nobel committee for inventing this IC. So the first thing that was created was the IC, which is an electronically controlled switch with one terminal as the controlling terminal, and the two terminals are the input and the output terminal, we can see. So depending upon the controlling voltage, it can give some input, or no, it can give the output. So after inventing the point contacts, a Bell Laboratories was the first who developed BJTs. BJTs, as we know, that they are more reliable and less noisy. Also, they are more power efficient. So when we need a uh, small device, small IC, we can easily include BJT for that purpose. So mainly BJTs were used to create ICs, which requires a small current to control the whole input output. Here the input is given at the emitter, and output terminal can be taken as the collector. So the current that is controlling the emitter and the control current between the emitter and collector is the base current. So the current in the BJT, this base current is very small. So we can use small current BJT base current to control large current between emitter and collector terminals. So this quiescent power dissipated by these base current draw even when the current is not switching. So with this leakage current, we can say the maximum number of transistors that can be integrated into single wafer is uh, the limits, right? So we cannot increase the number of transistor to any number just because of the leakage current in BJT. So to tackle with this problem in 1960, the MOSFET was the first MOSFET was used to replace the BJTs. So MOSFET was the transistor that has low leakage current. So if we have zero input output, if we do not want to control, we give the zero control current, there is no leakage current. So disadvantages make disadvantage make the IC more to include more number of transistors. So when we do not have this limitation of the BJT, that the number of transistors are to be limited due to the leakage current. So we can include a number of transistor. We can increase the number of transistor by including MOSFETs instead of using BJTs. So we have MOSFETs in two types. One is the N MOSFET and other is the P MOSFET. So we can use both of these MOSFETs in the ICs. So this was the first MOSFET. This was the first MOSFET that was used, which was using semiconductor silicon. The gate was of aluminium. So if we say the side view of this one, it was like aluminium, silicon oxide, and silicon. Silicon oxide is acting as the oxide for the MOSFET. Aluminium was the metal which was used for the conduction, and then silicon is used for as the semiconductor uh, for the source and the drain. So this was the first MOSFET that was uh, given by KAG in 1960. So this gives interface with silicon oxide interface, which was using uh, some metallic contacts for the extraordinarily good contacts. So in 1963, the Franklin Wellness described that the logic gates can be used using the MOSFET. The logic gates that can be used for the MOSFETs. That means we can create some logical structure with the MOSFETs. For this one, they have used both the P and N type of the transistor. Because they are using P and its complementary N type MOSFET, so they name it as complementary MOSFET or CMOS technology. So with using this CMOS technology, we can create the logic gates. So when we can create logic gates, we can create a number of uh, digital circuits. So MOS ICs were attractive due to its low cost. Also, the area that is occupied is also less. So this makes the whole fabrication at a larger extent, and the process was simpler. So earlier, the commercial process that was using only PMOS transistors, they have a poor performance. Also, we need their throughput was very small, means the number of ICs preparation was difficult. So it was very difficult to prepare the, the number of ICs. So the process using NMOS transistor became common in 1970s. So after that one, we were using most of the time CMOS and the NMOSs, non-MOSs, which has better performance, better yield, and also the reliability is also good. The more important thing is that they have lesser leakage current as compared to BJT. So when the number of ICs, when the number of transistors in an IC were increasing in 1965, Jordan Moore gave a law based on his observation. He observed uh, a plot between the number of transistors and uh, the the number of transistors in per unit area with time. So he creates a graph between time on one axis and number of transistors on the other side. So with this observation, with this graph's observation, he found that the graph is almost linear, increasingly linear. So with this one, he found that the transistor count in in an IC were doubling every 18 months. After every 18 months, the number of transistors in an IC were doubled. For example, if we take IC 741, if we take an IC of op-amp, if today op-amp is using 5 number of transistors, then after 18 years, uh, we can create more number of op-amps in the same area, because those 5 transistor in one op-amp will be taking lesser space in an IC. So basically, Moore's law were driven by scaling down the size of a transistor and to a minor extent by building large larger chips. That means we can include number of transistors that were increasing. As a result, the size of the IC was increasing. So the size of ICs are increasing and the functionality of ICs were also increasing. The same IC can be, on the other words, we can say that the same IC can be reduced, same IC will have reduced size with the same number of transistors. So if we say, if we are discussing IC, then we can see that this is a typical IC which uh, which contains some silicon chip here and metal contacts at the other sides for the connection between the ICs. This is a real IC which has this as silicon chip, and the wires are taken for the legs of these IC. The IC has many components. They can be active as well as the passive component that can be that are mostly fabricated on one single silicon plate, also called the wafer, or any other semiconductor depending upon our choice. These there can be some active components like transistors, diodes. There can be passive components like most of the resistance and the capacitors were used in the IC. Inductors are excluded in preparation of the IC. So when this IC is silicon chip is there, this the size of this one is smaller one. If we want to include it to connect with the other lamped circuit components, then we have to take some metallic connections which are like this one. So these connections we can connect with to the other lamp circuits. There are a number of ICs depending upon the shape of this, depending on the shape of the IC. So how the IC is there and how these are connected to the external circuit. There can be a metallic can type of IC. For example, the most of the FETs are can be seen by like this IC. There are single transistors that are seen by this IC. The notch is there that is showing how we can calculate, how we can start the pin, how we can count the pin of the IC. Then there are some ceramic flat packages IC which have flat in the surface and the connection are given out like this one. So we can connect it easily with the external circuit. The mostly DIP, dual in package, dual inline package ICs are used in the process where we need to change the IC regularly. We can have the base of the IC where we can put this DIP ICs. For example, all the ICs that we see in our lab experiments are generally DIPs. So this DIP has a small chip inside this one, and all the wires that are shown here, those are taken from that chip for the connection with the external lamp circuits. The other part, that black part that we see is the outer covering. They are generally for the that is generally the packaging of the IC that provides the insulation between the different metallic wires as well as uh, uh, the insulation with the outer world. Also, they protect the silicon chip from the external environmental as well as the all other effects. So, with this ICs, there was the first ENIAC first computer that was prepared with the help of the vacuum tube. It was 1946, which was is the size of more than a hall. So this has a shorter life. Also, the size was very high. The storage capacity was low as compared per unit area was low because of the huge size of the device. the power consumption was high. Also, the leakage current was also high. The controlling of the vacuum tubes were not as accurate as the solid state devices. So with this one, uh, with this greater uh, large size computer, the miniature computers, today's laptop has covered a large journey by creating some solid state devices. The transistors, the resistors, the gyrators, the capacitors, all these were created in a single IC. So with the increase, we have a pocket size PC made of semiconductor or solid state devices, which has much higher performance with the low level power consumption. So anything that was done by a large computer, today we can do it with a very smaller size structure. For example, this is an IC which was in 1970, which was taken as a DRAM, dynamic RAM, for by the Intel for connection in the uh, memory unit. So this was the microprocessor unit, which has the layering also, layering of the different devices one over other. So this IC has a thousands of the semiconductor structures in one IC. Similarly, this microprocessor has more than 1,000 transistors in this IC. So with this increase of the number of ICs per unit area, we can divide the level of integration in an IC. Depending upon the level of the integration in an IC, we can classify it into small scale integration, medium scale integration, large scale integration, and very large scale integration, which is VLSI. If we classify these, the number of gate, depending upon the number of gates in per IC, if number of gates uh, in an IC are less than 10 gates, then this is called the small scale integration, SSI. If number of transistors are more than are approximately or less than 10,000, 1000, then it is medium scale integration. From 10 to 1000 gates, it is called the medium scale integration. For large scale integration, the number of gates were increased to 10,000. So anything which has a number of gates between 1000 to 10,000, those are known as the large scale integration. For a very large scale integration, there are no more than 10,000 transistors in an IC, then it is called a very large scale integration. For example, some examples are given like 741 and inverter IC, not gate IC 7404, that has 4 gates. So these gates are uh, these gates uh, are classified into small scale integration. There are there are 4 uh, gates, so there are 4 inputs and the 4 output in that gate. Then there are some counters which are also using gates, like 74161, which is a counter IC. This counter has less than 1000 gates, but are more than 10 gates. So this is classified as medium scale integration circuit, or MSIC. Then large scale integration circuits, which are generally microprocessor units, memory units, microcontroller units. So all these units are the large scale integration. More than this one, if there is any specific purpose IC, those are generally classified into VLSI, very large scale integration. For example, most of the calculators that are using microprocessor as well as the memory units are have more than 10,000 gates. So those are classified as the very VLSI gates. So if we review the whole history, then we can say that right starting from the initial 90s, we have started with the vacuum tubes, then also the solid state devices. Solid state devices. Uh, 20 years we cover this vacuum tubes to prepare a computer. Then transistors were used, BJTs were used, which were replaced by MOSFET. Then MOSFETs were used in the IC. So with the increase in the silicon technology, the density became higher and higher. The low power was used, and the speed was increasing. So with this one, we can include more number of transistors in an IC. So after 1960s, when an IC was created, it was the density of the devices in that IC was increased. So this was including more number of transistors. So the IC was going to the large scale integration. Large scale integration is also uh, uh, after Moore's law, we increase the number of transistors per unit area. So with this one, the large scale integration was increasing to very large scale integration, and then very large scale integration is also increased from the ultra large scale integration. This is not only because of the number of transistors, this is also the change in the technology from the semiconductor devices to the vacuum tubes, the solid state circuits that are included in the in the uh, ICs. So from all the perspectives of speed, low power, integration, reliability, power, we are increasing the all parameters of the IC day by day. So this is all about the history of the IC. This we have discussed at how IC was started and how it has reached to a place where we can uh, take IC into small into very large computers. Thank you.